Okay, hello everybody, and welcome to the Elmer-FOAM webinar series. So today starts the fun stuff. So you have been listening to 3 rather boring presentations from Elmer team, and now we go to something a little bit more interesting. So the first contributed presentation will be given by Juris Venchels, and it will be about Elmer-OpenFOAM library, for which Juris is the main author of. And Juris is currently in AUF Consulting, and he holds a Master of Science from KTH in electrophysics. And during his studies, he was also a visiting researcher at Los Alamos National Laboratory. So he knows his stuff, I can assure you. So we also have our technical supervisor here, Mikael Kanerva, who will start with a few technical notes or on the beginning. So
yes, hello everyone. Yes, thank you, Peter. And hello everyone, and welcome on my behalf as well to this webinar in the Elmer-FOAM series, Elmer-FOAM series. Just a few practicalities again, and especially for those who are here for the first time. We operate on the basis of your microphones being mute, and you can then address the presentation or the presenter by writing your questions in the Q&A box. The Q&A function is at the bottom of your screen. So please write all your questions related to the substance of the webinar in that Q&A box. And also we have a chat that's usually for just general announcements, and of course you can then if you want, there's an opportunity to have a general discussion in the chat window if so needed. And otherwise, this webinar is recorded and will be published on our Elmer-FOAM YouTube channel within 1 week. I'll post the address in the chat window in a moment, and you also see the URL address for the presentation slides, which will also be available after this webinar. So on my behalf, I welcome Juris Venchels as well, and hand over the word to him.
Hi everyone. It's nice to present to such a wide audience this work that I have done like about 4 years ago when I was a PhD student at the University of Latvia. So yeah, let's take a look how electromagnetics can be solved wisely in OpenFOAM, or CFD can be solved wisely in Elmer-FOAM from my perspective. As our story usually begins with motivation. So why this library has been developed at the first. And motivation was as following. Idea was to solve industrial and also scientific MHD problems. MHD stands for magnetohydrodynamics, which basically, like in simple words, means controlling liquid metals with time-varying magnetic fields. And those magnetic fields, time-varying magnetic fields, can be created either by magnets that are changing directions or moving, or with alternating currents. And those are 2 examples that then demonstrate what work I did when I was a PhD student. So on the left, we see electromagnetic levitation problem. Here in the middle, we have liquid metal that levitates between 2 oppositely directed coils with opposite currents. And on the right, we have like a bucket with liquid metal. All around, we have windings, and basically time harmonic current generates a field. Field interacts with liquid metal, and its surface kind of is making those small waves. So, and basically, when this goal was set to simulate those type of problems, like it was kind of clear what is needed to do that. Like from fluid dynamics viewpoint, we might have very high Reynolds numbers, particularly in that levitating case. As you see also saw before in pictures, that all those liquid metals applications very often have free surface. So there should be some method to cope with that as well. And different material properties that are dependent on temperature. Like in liquid metal case, that could be like viscosity. On the right side, all requirements from electromagnetics. So almost all problems are solved in 3 dimensions. And for that, AV, and also like including eddy currents. So for that, AV formulation is kind of probably one of the best currently available. Conductivity dependence on temperature. So liquid metals, once they melt, their conductivity is temperature dependent. And the term V cross B is basically kind of currents that are generated when a fluid with velocity V moves along magnetic field B. So there are additional currents, additional forces involved when such liquid metal kind of flows in magnetic field. And those currents need to be also considered when solving electromagnetics. Yeah, and what kind of is common for fluid dynamics and electromagnetics, almost all problems are 3D transient with very complex geometries, and advanced post-processing is very common, like to generating complex meshes. Problems are quite large, difficult to solve, so parallelization is very important. And at that time when I started, kind of user support and community was very important to me to consider, because like there was no other people who could help me, direct me in which direction to move. So it's good to kind of get pieces by pieces of information from all other people. Yeah, and at the beginning, it was clear that the right tools to simulate MHD problems was OpenFOAM and Elmer, because OpenFOAM, as you know, is kind of the most popular CFD software, open source software, and it has capability to model high turbulence flows, and also it has such a finite volume, finite like methods that are WOF methods that are for solving flows with free surfaces. So that was a nice feature. On the other hand, like Elmer at that time when I started was quite capable to solve electromagnetic problems. Now it's much far better than it was 4 years ago, but at that time it was kind of enough for me. And again, what unites both softwares, OpenFOAM and Elmer, that they are highly parallel software packages that are using so-called message passing interface to kind of decompose and communicate between different processors, those data that is distributed. And yeah, what else I found was that both OpenFOAM and Elmer have quite good interpolation features that allow to interpolate data from one mesh to another mesh. And yeah, both software packages are quite mature and robust, which kind of was a big thing for me. And of course, kind of it would be easiest probably to implement such coupling between OpenFOAM and Elmer in an old-fashioned way. Just write everything in files, and another software opens, reads files, etc. And there are, of course, some researchers who did in such way, like coupled even commercial software packages. But I consider that it's very kind of primitive and very slow comparing to message passing interface approach, which allows us to kind of transfer this data between different processors, different like softwares, different pieces, like directly without storing to files. And it is kind of a big advantage. So it was kind of clear that MPI is a good choice for such highly efficient coupler that is needed to couple OpenFOAM and Elmer. But enough with the motivation. Let's talk about applications, what this tool can do. And applications that I will show you are kind of not only my applications, but also like contributions from other people who are using this nice tool and moving research as a research forward. Yeah, quick note. So from OpenFOAM side and from Elmer side, there are no restrictions which solver we can use, which solver we can couple. The only kind of limitation is that we can couple volumetrically. Yeah, later I will explain what it means, but to make it like very short, from OpenFOAM side, we can easily use like solvers involving different medium, like liquid gases, particles, and also Lagrange particle tracking. And from Elmer's side, so I already have used solvers involving like induction microwaves and different steady state and transient electromagnetics. Acoustics I haven't tried, but I'm sure that for aeroacoustics, this coupling also can be used. And what both softwares can do together also is to solve heat and different parametric dependence. So yeah, speaking about actual applications, one of my favorite and the first, almost like actually it was the second application, but it is kind of my favorite, is based on work that was done by my colleague. He experimentally did electromagnetic levitation. He did experiment and also did some simulation work. And here what you see is that basically he at the beginning puts a small sphere of aluminum between those two coils, and then turns on current in those coils, and liquid metal melts, and then as you can see it starts rotating. So very interesting how this metal behaves. So my attempt to simulate this problem was as following. So it was 3D dimensional problem. So here you just see the sketch of geometry. So at the beginning we have aluminum melt, and yeah, actually it was melt. I didn't start from solid. And we have coils. OpenFOAM mesh is smaller than Elmer mesh. So here, this OpenFOAM region corresponds to like this internal region in Elmer. So because magnetic fields need to be closed somehow, so domain for electromagnetics typically is larger when we couple Elmer and OpenFOAM. For OpenFOAM, boundary conditions were quite simple. So it was atmosphere, like just pressure and velocity driven boundary condition, so that fluid can exit if needed, and gas can easily flow inside and outside this domain. So yeah, and simulation results from the top, from side, and velocity distribution. So you can see that like flow is very complex. And this problem was solving for, I guess, 2 weeks on 16 core computer with 64 gigabytes of memory. So yes, and yeah, it is basically like it was solving repetitively OpenFOAM did a couple iterations, then updated electromagnetic field according to shape of this liquid metal, and then again did OpenFOAM simulation. Another case from MHD, but from another my friend from University of Latvia is liquid metal pump. So basically we have a pipe that bends, and inside this bending point, we have rotating magnetic systems that rotates, generates Lorentz forces, and basically drives this fluid through this channel, creates a pressure drop. And another much newer application of EOF-Library for MHD is liquid metal bubbles in liquid metals, again from colleagues from University of Latvia. Their setup is that they have kind of bucket with liquid Gallenstein, liquid metal, and here they have like two large magnetic systems and magnetic wire. And they do computer simulations with OpenFOAM and Elmer and produce those nice pictures. So when bubbles are going up, if there is no magnetic field, then they have larger spread. They're kind of oscillating. And when there is introduced magnetic fields, then they trajectories are kind of smoother. They go directly, almost directly up. Yeah, so there are also other applications of this library. There was one research article made by researchers from, I guess, Thailand. You can check if you want. So they have magnetic microwave generating device, waveguides, and here somewhere in the middle they put a bucket with water, and magnetic microwaves are kind of hitting this water from the top. So in this video, we see my simulation. So we have electromagnetic field, heat distribution in water, velocity field. So here on the top, we have Marangoni effect. Marangoni effect is surface tension dependence on temperature and temperature distribution. So again, we have like properties, electromagnetic properties that are dependent on temperature, also fluid dynamics properties dependent on temperature, and like all those electromagnetic and fluid dynamic kind of models need to be coupled together. So we cannot solve, in this case, electromagnetics independently from fluid dynamics, etc. Another case is more industrial-like for industrial microwave heating of different liquids. So this is a picture from an actual patent from researchers at Iraq from United Kingdom. And basically we have a pipe, we have a chamber, and a magnetron antenna that enters those microwaves in the chamber. And it's very interesting application because again it involves like temperature dependent material properties, and this is kind of truly multiphysics three-way coupled problem. Like for electromagnetics, we have permeability dependence on temperature, and for fluid dynamics we have viscosity, density, and thermal conductivity dependence on temperature. So yeah, it's kind of very interesting that there are also like not many, I would say, like commercial softwares that could do this microwave and fluid dynamics coupling, especially for highly turbulent flows. So this is kind of interesting application. Another kind of direction in which EOF-Library developers like me and other users were looking for was different cooling applications of electrical devices, like, for example, electrical motors. So inside this nice looking electrical car made by Nissan, there is an electrical heart inside that is made from like aluminum, and like this is electrical motors, of course. And the electrical motor from outside, it has like liquid cooling jacket, and inside that liquid cooling jacket there are like places where fluid flows and removes excess of heat from this motor. And what is interesting, like for copper, this electrical resistivity is quite dependent from temperature. Like increasing temperature by 60 degrees, we may have 24% increase in losses because resistivity gets larger. So it's quite important for electrical devices to consider temperature effects, not only on efficiency, but also on like how reliable is this device, whether we have some hotspots. So yeah, it was kind of very basic model developed just for testing purposes by me, then Jane Keranen and Aku Karvinen from VTT. And the idea was that we can take a very basic electromagnetic, like stator part, outer part from electrical motor, where currents are flowing, and we consider that the most heat is generated in that outer part of the electrical motor. Then we have aluminum and water jacket that cools this motor. And yes, it was kind of possible to couple OpenFOAM conjugate heat transfer solver with Elmer electromagnetic solver and send to OpenFOAM like Joule heat, and OpenFOAM sends to Elmer temperature. So we have two-way coupling, and we are able to reach very accurate steady state by updating temperature and Joule losses iteratively. And it was found that, yeah, kind of like considering resistivity dependence on temperature plays an important role in those electrical heating applications. And of course, there's one more case to demonstrate to you, also one of my favorite, because there is a company, Czech company, PlasmaSolve, who are doing plasma physics simulations. They have quite substantial like tool set to solve plasmas in different regimes. They are kind of, for those who are familiar with plasmas, they know that they're like different kind of methods applicable only in very narrow kind of plasma regimes. And they built their like simulation tools on OpenFOAM DSMC model, Lagrangian particle tracking models, and of course using Elmer electromagnetic capabilities. So if you are kind of interested, I suggest you to go to their webpage and take a look how nice like simulation work what a nice simulation work they have already did, and how smart those guys are. Yeah, so let's talk about how this EOF-Library works and what it can do and what it cannot do. So basically, EOF-Library, it is very simple library for OpenFOAM and Elmer. Like on OpenFOAM side, we just have like basically two files, Elmer.c and Elmer.h, that have all like coupling functionality inside and provide OpenFOAM with ability to talk with Elmer. And on Elmer side, we have two solvers. Like you probably know that in Elmer, everything is like divided in different solvers. You may have solver for calculating divergence. You may have solver for calculating electromagnetics. everything is like solver, and you just stack those solvers together and obtain that functionalities that you need. And similarly, like here, EOF-Library is for Elmer is just a set of two libraries. One is for communicating fields from Elmer to OpenFOAM, and another is for communicating and of course interpolating. I forget, very important to say, is that we are not only sending, but we are also interpolating, yeah, from OpenFOAM to Elmer. And yeah, the thing is that when we start simulation, then we need to initialize some data structure that could later on help us and speed up this interpolation and data transmission. So every simulation, when we start Elmer and OpenFOAM, we call like OpenFOAM to Elmer routine. And in this case, Elmer sends coordinates where it needs field values. It sends those coordinates to OpenFOAM, kind of asks OpenFOAM, hey, could you please kind of do mapping between my coordinates and your coordinates, and let's create like a strategy how we will later on do this interpolation and data transmission. Yeah, OpenFOAM searches for cells where Elmer, corresponding Elmer points are, and not like sends back information to Elmer where that it has found those points and on which processor those points are located. And OpenFOAM stores point to cell relation so that later on we don't need to repeat this initialization again. And from Elmer to OpenFOAM side of view, it is very similar, but the difference is that in this case, Elmer is not storing point-to-cell relation, but it is constructing so-called interpolation matrix. So it's just nice, beautiful matrix for interpolation. And when we need to interpolate some field from Elmer to OpenFOAM, then all what we need to do is just nicely multiply matrix by vector. So it's super fast operation. It's important to tell that currently EOF-Library does not support adaptive meshes, but in principle that could be introduced. The only drawback would be that every time we change mesh for OpenFOAM and Elmer, then we would need to recreate this point-to-cell relation or construct a new interpolation matrix. Yeah, and when we run simulations, then it is like, I guess, called leapfrog. So basically probably leapfrog is a different strategy, but okay. Elmer computes its problem, sends some fields to OpenFOAM. OpenFOAM then does computation, sends back to Elmer. So we have basically Elmer, OpenFOAM. So they're solving one after another. And on the right, we see that there is a strategy illustrated for solving MHD problems. So in most cases, OpenFOAM is, I call it kind of leading software that takes control over Elmer, because like in CFD, we have much smaller time scales, yeah, turbulent flows and sudden velocity changes. But from Elmer side of view, so we just need to update very often like steady state solution. So OpenFOAM, at least for MHD, takes control over the whole simulation. It solves fluid, and then it there should be some algorithm to figure out whether we need to update Elmer field or not. If yes, then OpenFOAM prepares to send data to Elmer. Elmer then recomputes electromagnetic field and sends back some values that is needed to OpenFOAM. And this cycle then repeats as long as OpenFOAM simulation is running. In the code, this coupling or data transfer looks as following. So on OpenFOAM side, somewhere in the code, we have MPI receive comment, and in Elmer side, in Elmer-Library, there should be some corresponding MPI send comment. So for every receive in OpenFOAM side, we have send in Elmer side, and basically this when we want to send from Elmer to OpenFOAM, then in the software it looks as following, so that we enter this code, then it selects a variable that needs to be communicated, then it applies interpolation matrix. So here it is apply projector. So it does interpolation and sends data to OpenFOAM. And in this place, OpenFOAM, like here, it was waiting until the message from Elmer will come to OpenFOAM. Once this message is received, then OpenFOAM receives this message and continues with simulation. So it's very kind of simple. Yeah, and both softwares, Elmer and OpenFOAM, are run simultaneously. So we use this MPI run kind of wrapper for parallel applications that specifies the number of Elmer cores we want to run. For Elmer, it can be starting from one core. There is no limit how much we can maximum use Elmer cores. And for Elmer, there is and we put semicolon, and then we specify how many cores we want to use for OpenFOAM. And for OpenFOAM, we cannot use less than 2 cores. It's just kind of hard-coded for OpenFOAM. And the case with running that runs on 16 cores would look, as following. So although it will run on 16 applications of Elmer and 16 applications on OpenFOAM, it will utilize only 16 physical cores on computer, because while OpenFOAM, for example, is calculating, Elmer is waiting, and then they just switch. So kind of we reuse quite efficiently or computational resources. Yeah, and for every MPI send, there is MPI receive on OpenFOAM side and vice versa. Quite important for those who are doing research, how accurate and powerful is this library. And to do this kind of analysis, like a few years ago, I did a unit cube test. You can find a research article that describes it in more details and also describes different interpolation strategies and algorithms. You can find in article which starts with EOF-Library, but like in very short, like it was tested with 3 different sizes of unit cubes. There was distribution initialized, and we measured what is relative error depending on mesh size. And what we found that when we interpolating from Elmer to OpenFOAM, then you can see that reducing mesh size twice reduces error almost like 4 times. Yeah, so this accuracy from Elmer to OpenFOAM is kind of almost second order. And when we interpolating from OpenFOAM to Elmer, then this accuracy is worse. It is slightly above like linear accuracy. So reducing mesh, like making mesh 2 times finer, we get slightly more than 2 times more accuracy. And of course, if we would consider that this mesh can be refined even more, then we get closer to 0. And from performance viewpoint, quite large unit cube simulation was run, and it was strong scaling test. So this unit cube mesh size was fixed, but only core number was kind of changed. And what we are interested is what is time to initialize this coupling functionality from OpenFOAM to Elmer and from Elmer to OpenFOAM, and how much time it takes during the runtime to communicate, interpolate and communicate those fields. So what we see is that for quite a large mesh, initialization time for 4 cores can take considerable amount of time, but we see that it scales quite well. Yeah, up to 256 cores, this initialization time reduces significantly. And this initialization time is called only once when we need to establish connection between OpenFOAM and Elmer. But with runtime, things are even better because, like, for those 256 cores, we have interpolation and communication time less than a second. Yeah, for such a large mesh, less than a second to interpolate and send fields from one software to another, I think it's quite fast. So the conclusion is that this coupling library, in most cases, will have very, very, very small performance overhead comparing to computational time. And by computational time, I mean solving physics. So yeah, for those who are attending here, the question probably is, okay, so it looks very nice. We want to start using this software, so how to get started? My suggestion is as following. So before you know Elmer and OpenFOAM on good level, almost like programming, almost developer, I do not suggest to start like directly with this coupling library. First, learn Elmer and OpenFOAM, and that can be done by like a bunch of materials exist, like different documentations, tutorials, forums. Once that is done, learning Linux is important because if you would like to use a full functionality of EOF-Library, you would need to know how to run Linux, like from terminal, how to compile software. And once you are familiar with Elmer, OpenFOAM, and Linux, only then try yourself coupling library. It's better to start with test case that is provided already in together with the software. Levitation 2D. I will later demonstrate this test case. Also take a look on MHD interFOAM, as this is OpenFOAM solver that solve this test case. And by using this solver as an example, you will figure out how to take any OpenFOAM solver and modify it so that it can be used together with Elmer. Yeah, so it is important that you know how to make changes in OpenFOAM source code, because like you will need to modify those solvers. And for like some reference, you can use this article called EOF-Library, open source Elmer-FEM and OpenFOAM coupler for electromagnetics and fluid dynamics, written by me, Peter Rabak, and also my colleague from university. Yeah, use this as a reference, and if you use this EOF-Library, then do not forget to reference to this article. If you don't want to do it yourself and want to get advantage over other by solving your problems faster, more efficiently, then you can use my consulting services. I'm located in European Union and running my private company that is kind of officially registered, and Yeah, and I can help with applications involving microwave heating, induction heating, and different electrical heating applications. Not only EOF-Library, but also for Elmer. Yeah, so contact me if any help is needed. And now I think it's demo time to demonstrate one very simple application of EOF-Library. I'm now fighting with Zoom. Give me a second. Yeah, so everything is available on GitHub repository. Current and official, let's call it, version of EOF-Library is stored on my personal GitHub. And yeah, basically, once you download the code, then I suggest you to follow very, very simple instructions how to get started. And there are like two ways how to get the software running. One of those is using Docker containers, which I personally prefer to run on different parametric sweeps and also sometimes to run on cloud. And for development purposes, then I would suggest to compile it from scratch. And there are instructions in this README file how to do both. But in this case, we will just run those commands to get started with Docker. We basically, yeah, we enter, one second. There is EOF-Library that already has been downloaded from GitHub. We create a directory where we want to run those test cases and run Docker command. So with Docker run, here we specify host IDs so that we do not need root permissions inside Docker container to install software. And it is much safer to do in such a way because Docker is nice, but also very dangerous tools that can destroy your system. With this command, we tell that we want current directory from our host machine to mount to this directory inside Docker image. And this is the name of Docker image that we are going to use. So EOF-Library has some Docker images stored on Docker Hub. One of those is with older Elmer version 8.4 and OpenFOAM 6. So we entered this Docker container and we call EF update. And this is just a script that has been already installed on this Docker image that pulls all updates from Git repository, updates for EOF-Library, and compiles Elmer part of the library and OpenFOAM part of the library. Then we enter EOF-Library folder and compile OpenFOAM solver, which is called MHD interFOAM. Those who are familiar with OpenFOAM, you probably know interFOAM. So MHD interFOAM is application that has been adapted for solving MHD with free surface type of problems. So now it compiles OpenFOAM solver. It takes some time. Then we will copy test case from tester folder to runs directory. And yeah, we enter this folder, set fields for OpenFOAM. Decompose par also is like decomposition for OpenFOAM. And Elmer grid decomposes Elmer mesh in two pieces. That's it. And then we can run simulation. So let's make a bigger screen. So what we see here is that OpenFOAM does a couple iterations, and then Elmer solves its electromagnetic part of the problem. Then again, OpenFOAM does a couple iterations, and Elmer updates electromagnetic field. And yeah, this kind of frequency, how often Elmer needs to be updated, like Elmer solution needs to be updated, is controlled by OpenFOAM. Later, I will show you how that can be controlled. So we will enter this result folder. You can see that we have very like typical structure, like we have 0, constant, processor 0 and processor 1, and system, which corresponds to OpenFOAM part of simulation, Elmer mesh, and a case C file corresponds to Elmer. So basically, we just have a copy of OpenFOAM and Elmer like in one folder. And then we create a temporary file for OpenFOAM and can visualize results even while simulation is running. So we will open OpenFOAM file where solution is decomposed. So we select decomposed case. And yes, so what we see here is, for example, J cross B is force that has been sent from Elmer to OpenFOAM. So it is kind of dynamic. Alpha melt corresponds to liquid phase of fluid. And I guess our simulation is already done. So it took about like only 53 seconds to compute this problem. So it's quite fast. And we will open also results for Elmer. For Elmer, we go to mesh directory, and you can see that Elmer results are decomposed. So we open PVTU, and here it is. So as I told before, Elmer domain is larger than OpenFOAM domain. Let's take a look side by side. So OpenFOAM corresponds to this internal part in Elmer kind of body, what that is inside Elmer computational domain. And if we look on fields, then J cross B, real part of J cross B is that value, that distribution that was sent to OpenFOAM. This is that value that was interpolated and sent to OpenFOAM. Here it is. And OpenFOAM sent to Elmer conductivity. Conductivity was equal to liquid phase multiplied by conductivity of liquid metal. So we can take a look that when Elmer did computation, then inside this region, it had this material with non-homogeneous conductivity. So that's, yeah. Very quickly about how to use software and how to modify. So library, inside library folder, pretty much you will not need to touch anything. What you will need to do is to modify solvers yourself. So basically you will take a solver from OpenFOAM and do some modifications. We can take a look, for example, on this MHD interFOAM. So yeah, at the beginning of this file, if you will compare with default interFOAM, you will see that these files are very, very similar. But the difference is that at the top we have this Elmer.h added, so that we access functionality. And you will find that here at the beginning of simulation, we have initialization of functionality for sending fields to Elmer, like from OpenFOAM to Elmer, and initializing functionality to receive from Elmer to OpenFOAM. And yeah, so basically what we do, we are creating like a C++, not structure, but class that holds all information about how those meshes need to be interpolated. So here we initialize that class, and with this sending corresponds to sending from OpenFOAM to Elmer, we send scalar, so similar can be send vector, and we provide that variable that we want to send. Similarly, for receiving class, we have here, for example, we have receive vector, and this is that vector that will be received from Elmer to OpenFOAM. And if we open test case that I have shown you before, CIF file for Elmer, then you will find that we have corresponding solver 1, which is OpenFOAM to Elmer. And when Elmer steps on this solver, then it knows that OpenFOAM will send one variable and here this is that variable, corresponding variable in the same order. This variable, electrical conductivity, is going to correspond to OF conductivity in Elmer. Then Elmer does computation, computes like magnetic fields, currents, and reaches solver number 4. And solver number 4 is Elmer to OpenFOAM. And here we have 3 variables. 3 variables corresponding to 3 vector dimensions of J cross B real part variable. So we are not here specifying vector as a whole, but by components. And it will send by components to OpenFOAM. And here OpenFOAM receives that field and starts computation. And inside while loop, here at the end, we have a requirement. This requirement tells when OpenFOAM wants Elmer to update electromagnetic solution. And if this requirement holds true, then, or also it is the last iteration, then this constraint, like if statement is called, and we again, every time we need to communicate fields, we send from OpenFOAM to Elmer electrical conductivity, then Elmer does his job, sends back J cross B, and OpenFOAM receives J cross B. So this just happens again and again and again. So yes, so as you can see that in Elmer side, you don't need to modify anything, just add solvers. And for OpenFOAM, you will need to modify solvers yourself. But other than that, like there is not such a big complexity once you learn how to use both software packages. That's pretty much everything I wanted to tell. So thank you, and let's discuss questions then.
Okay, do we have any questions? Please type them in. So if you have questions. Yeah, we have at least some questions from Christian Schubert. I think they are maybe not totally too related to EOF-Library. So are there any plans for implementation of volume conservative property interpolation in the future, for example, for Joule heating? So
difficult question. So I think all development that will happen with this library will be like based on some projects and project funding. So the question is as simple: if there is some interest, then also kind of involving some funding, then I'm more than interested. But if there is no, then kind of EOF-Library currently, at least for those problems that I am solving, kind of solves most of the problems.
Yeah, I guess in order to have that, we should know, like in Elmer's side, the like finite volume elements or their shapes. Now we only know the cell centers, so it is not sort of easily so doable currently. And the second question, I experienced that Elmer-FEM Whitney AB harmonic solver can become very unstable if the electrical conductivity fluctuates very strongly in the coupled field. And are there any solver settings you can recommend to circumvent this?
I use default settings, and it could be that when it fluctuates, then and like also the question is, it depends from either it's transient problem or it's steady state. I guess for transient it is more like severe, that effect when conductivity changes, than for steady state. Yeah, so I using default settings and only playing around with tolerances and making meshes kind of good enough so that it works.
Okay, maybe somebody in the audience would like to comment on these preconditioners, for instance, for the harmonic solver. Also, we have a raised hand, so Kaspars, do you have a question?
Yes, I have a question. Can you hear me?
Yes.
Yeah.
Okay. Yeah. Yes. Thanks for this great presentation and also the great tool. I have used both OpenFOAM and Elmer for various simulations, and where I see a great advantage of Elmer is to calculate complex heat transfer problems, especially involving heat radiation. Yeah, and again, a great advantage of OpenFOAM is doing complex melt flow simulations very efficiently. And the question here is about coupling complex heat transfer and complex flows. And in many cases with radiation, you need kind of coupling on surfaces, like specifying or transferring heat flow, which you calculate in Elmer, which depends on radiation, transferring this flow on a boundary to OpenFOAM. So do you see any potential here, or is this already possible maybe in partially?
Currently, there is no interpolation between surfaces, only volumetric. Difficult to say how this tool will change in the future. If there is some kind of interest to have also some coupling on the surface, that has to be kind of discussed.
Okay, so this could be a future implementation, but it would be quite a big work to do. Yeah.
I would say that even like logic how this coupling would work will be totally different. So coupling volumetrically and or on the surfaces, that would involve different interpolation strategies, and you may have like difficulties to match surfaces if meshes are not identical.
Yeah.
So I would say even that coupling on surfaces is more complex than coupling volumetrically.
Okay, so it would be maybe a different kind or a new version of library which would be needed here, if I understood you correctly.
Yes, that could be a new product.
Okay, is this something which is similar to the precise library? Maybe you have heard about the precise library, which is focused on coupling on surfaces, or is this something?
Yeah, I have heard about them. Not sure how well they are currently doing with Elmer. I know that they have a coupler like for OpenFOAM and
Yes.
Phoenix and other software packages. So the strength of EOF-Library here is coupling volumetrically.
Okay,
doing
I see.
it very efficiently and fast, and easier for user kind of to understand the logic and modify the code. So difficult to me to comment about precise, but I guess for those applications that I described in this my presentation, that EOF-Library probably is kind of more efficient for those particular applications.
Okay, yeah. Thank you for your comment. Maybe a short question to Peter, if you maybe could comment on the differences and advantages precise and EOF-Library. Would you say EOF is also in the future basically for volumetric coupling, and precise could be something for Elmer and surface coupling? Would you say this?
Yes, it seems so that this is the sort of division that that EOF-Library is for volumetric coupling and precise is for the surface coupling. And going back to the original case, maybe you could think of a sort of a partially overlapping like temperature fields. Like there are different domain composition methods, and you could sort of have an overlapping sort of method as well here, sort of to mimic sort of some boundary.
Yeah, I think that's a great idea. One very simple possibility would be to introduce a thin layer, yes, where you have a volume heat source. Yeah, so you do not need this boundary logic, but you can have a thin layer on the surface, which is kind of still a volumetric coupling. Maybe that could be an idea.
Yes, yeah? Yes. Then you could use the library of URIs. Yes.
Yeah, yeah. Okay, thank you.
And do we have any other questions? You can raise your hand. We are not that crowded today, so no hands. Okay, we have a hand there. Okay. So, Elis, please. Elis Takala, you can. I hope you can talk now. So.
Can you hear me?
Yes.
Good. Yeah, sorry, I was muted. So thank you very much for the very interesting presentation. Especially the hands-on part was very interesting. What I was wondering is how you control the different partitions, because I guess you have to partition both Elmer and OpenFOAM, and so that they would be similar as possible.
So from library standpoint, they don't have to be similar. From efficiency viewpoint, especially when you run like large jobs, that would play a role, like probably.
Yeah, I was thinking about the efficiency, that if they are in different machines and then they have to send the information from one to the other. Am I understanding this correctly?
Very good point. Yeah, about sending data to different machine. Then this partitioning would play some role, but as the case with this unit cube has shown, that even when you run on like it was 256 cores and 60 core machine, so it was like multi-machine, multi-node system, and even then this interpolation and communication time was below a second. And considering, like comparing to computational times, that typically is for such a larger meshes, like even in seconds, tens of seconds, or even minutes, then this in overall like does not play such a big role. Yeah.
Okay, that's very interesting. So basically, you don't really have to care about which part of the mesh is going to which machine.
Typically, I don't consider any optimization in this partitioning. It is important to partition wisely from physics standpoint. Yeah, so that like in OpenFOAM, you may have like evenly distributed number of cells between processors, and in Elmer maybe that plays a role when solving physics. But I guess from coupling and interpolation perspective, that's not that critical.
Okay, thank you. Then a little bit off topic, I was wondering how much power you had in that induction heater. Do you remember?
In which exactly?
The first one you showed, there was this aluminum ball that was levitating, and then you had these coils and you were heating it up. I was wondering how much power you need in that kind of setup.
To levitate.
To run that experiment, because I've been experimenting myself a little bit, and I was not able to get through the melting. I mean, I was not able to melt the thing. But do you remember what was the power?
I don't remember, but I will send you an article.
Thanks.
And it is interesting that that colleague from University of Latvia, he has solved and also did experiment with 400 grams of aluminum, and I guess even more. So it's quite a large piece of metal that was levitated. But that electromagnetic system, it started to be more and more complex, like multiple inductors, multi-frequencies. So those who are interested in levitation, I suggest you to search for articles by Sergejs Spitans.
All right. Yeah. Thanks a lot, Juris.
Yeah. Thank you, Alice.
Okay, I don't think we have any unanswered questions, so I think we can call it a day. And thanks, Juris, again. It was very, very interesting and very, very sort of impressive at the same time. So thanks, and we will continue this. Sorry, I should share the screen. Okay, so we will continue the webinar series soon. Here you will have some information where the material will be available or is already available. I think also Mikael sent the information to the chat, so you will find still, if you copy paste the stuff from there, you can find it there more easily. We will continue next week, and then actually the person who asked the last question, Eilis Takala and Fredrik Trilod, will be talking about electrical circuits with Elmer, and I think they will have some very nice applications. So the impressive applications will continue. So, which we are very happy, because our own applications, they were on the boring side. So it's good to have the visual effects included. I think with this, I will say, well, good evening or good day or whatever you are in your time zone, and maybe my colleagues would also like to say goodbyes. So, Juris, maybe you want to, and Mikael, you maybe want to say goodbye for our listeners. So thank you for joining us, and see you next week on the same time, same place.
Yes, thanks on my behalf as well, and hope to see as many of you as possible on the 8th. And this webinar, of course, was recorded, and we'll have it out. We have 3 already out, and this 4th one now will be out. Or is it even 5th one? 4th one, sorry, will be out within a week to view on the our YouTube channel on the address that's in the chat window. But to everyone, have a very nice afternoon on my behalf as well, and have an enjoyable Easter.
Just want to say thank you for everyone who attended this webinar.
Okay, so it looks like these are the finishing words for today. And so it's over and out, and we will end this webinar in about within a minute. So it's goodbye for now, and see you in 1 week.